In 4.5, we'll quickly review the theorems we've already talked about in class. We began with Rolle's theorem, talking about instantaneous rate of change, which is the tangent. And if we have a specific case where our function starts and ends at the same y coordinate, so f of a, one endpoint y coordinate, is equal to f of b, then there has to be some place between, there has to be some place C where we will come up with a tangent that is parallel to the secant. The secant between the endpoints is horizontal, so the tangent line would have to be horizontal. In our second drawing, if the secant is horizontal, there has to be at least one place, and those values would be our C values. So in the first picture there would be two of them, and in the second there would be just one. So there has to be some value C where f prime of C is equal to 0 for at least one value of C somewhere between A and B. And then we said, well, what if we just tipped our vision a little bit here? And what if the two endpoints weren't horizontally across from each other? So our secant line now is at some different slope, but wouldn't the same thing still be true? To get, if we have a differentiable function, so meaning that it would be continuous and no corners and no discontinuities, if we have a continuous function, then somewhere along the way there has to be at least one place where the tangent would be parallel to the secant, and these would be our values of C, the places where the tangent is parallel to the secant. And what that looks like algebraically is we want the derivative, this is the slope of the tangent, to be equivalent to the slope of the secant. Well, the slope of the secant we know is our endpoints, our y2 minus y1 over x2 minus x1. So somewhere the slope of the tangent is equal to the slope of the secant. And our next version of that is just cross multiply, move one term to the other side. All right, the rest of these we've heard before. If our first derivative is positive for every value in an interval, then f is increasing on that interval. And if f is less than 0, then it is decreasing. Our first derivative test, if c is a critical number of a continuous function. So make sure you're paying attention to the hypothesis in each of these. So if f prime changes from positive to negative, that means the original function f was rising and then falling. So if it rises and then falls, then f of c is a local max. And if f prime changes from negative to positive, that means that f itself was falling and then rising. So then f of c is a local minimum. And if f prime does not change signs, then it is not a local extremum. And when could that happen? That could happen at a saddle point. So our typical example is x cubed. We know that there's a place with a horizontal tangent, but there's no extremum there because the first derivative does not change signs. For concavity, if the first derivative is increasing, then f is concave upward, and if f prime is decreasing, then the original graph is concave downward, and that is equivalent to thinking about the second derivative. If the second derivative is positive, then it is concave upward, and if the second derivative is negative, then it is concave downward. And our points of inflection, if this point c comma f of c is a point of inflection if the function is continuous and there's an open interval around c where the graph is concave upward from the left side to c and concave downward on the other side from c to b. And it could be in either order. So we can shorten that and just say that we have an inflection point if concavity changes. So if the second derivative changes sign on a continuous graph. All right, the second derivative test, we don't use it as often, so it's important that you study and remember this. If we have a first derivative equal to 0, remember this means we have a horizontal tangent, and f double prime is less than 0, that means that f is concave down. So how can you have a horizontal tangent in a concave down section? You would have to be at a local maximum. And if we have a horizontal tangent in a concave up section, the only way that can happen is if we have a local minimum. So if you can find a place where the first derivative equals 0 and the second derivative is negative, then you can tell the concavity of the function. The second derivative test does not work if the second derivative turns out to be equal to 0. So then you would have to go back and use the first derivative test. All right, the extreme value theorem, we just heard this in the previous assignment. If a function is continuous on a closed interval from a to b, then a global max, and we'll call it c f of c, and a global min, we'll call it d f of d. You could put whatever you wanted to here for variables. Must exist for some c and d in the interval. All right, so they could be at the endpoint. So notice that c and d could be at the closed endpoint. So c could equal a, for example. And the closed interval test, remember what you had to do in the previous assignment. So when you have a closed interval, the global extrema can occur at critical numbers or at either endpoint. They have to be closed endpoints. So you must compare all of those y coordinates to find the global extrema if you have a closed interval. All right, and just a quick reminder now that we have MVT, the mean value theorem, and EVT, the extreme value theorem, to remember that earlier in the year we had IVT, the intermediate value theorem, and it said if f was continuous on an interval, then for any target number n between the y coordinates of the two endpoints, there has to be some place in the open interval where you hit that target value. So we said, how could you get from one y coordinate to another without passing every intermediate y coordinate in between? So you'll want to make sure you keep reviewing how to write an IVT argument. All right, here's our visual demonstration of concavity. If you look at these tangent lines, what's happening to the derivative, what's happening to the slope of each of these. So you can see we start out with very negative slopes, and then they head to slopes of 0, and then they become positive. So slopes are increasing is the same as saying that f prime is increasing, is the same as saying f double prime is positive, and that is the same as saying that f is concave upward when the slopes are increasing. And look at what's happening with these tangent lines. The slopes start out to be very positive, and then they go down to 0, and then they become negative. So same situation, of course, slopes are decreasing. Would mean that f prime is decreasing, which would mean that f double prime is negative. And that would mean that the original function f is concave down. So you want to remember that all of those situations are synonymous. All right. So let's see. I think I've lost part of my problem here. Let me pause a second. All right, I'm back. I had covered up question 13, so I just copied it here on my page. So we're asked to use the first derivative test. There's a typo, by the way. We should have open endpoints on the interval from negative infinity to infinity. So we want to find the first derivative here, 3x squared minus 12x plus 9. And we can set it equal to 0. We can factor a 3. And we could divide both sides by 3, in fact. You can do that if you wish. And notice then that we come up with two critical numbers, positive 1 and positive 3. So we know that the first derivative can only change signs at 1 and 3, and they're both single roots, so we expect the intervals to alternate. Remember that it will bounce at a double root. So we next have to check our intervals. So we're using all real numbers. So we want to test what's happening on the interval from negative infinity to 1, and what's happening on the interval from 1 to 3, and what's happening on the interval from 3 to infinity. And if you look at your first derivative, and if you look at your factored form, let me put this back into f prime of x notation here. So if you think about testing a number that is smaller than 1, then can you see that both of our factors, think for example of negative 10, both of our parentheses would be negative, so we would have the product of two negatives. So we know that on this interval, f prime of x will be greater than 0. And if we choose a number between like 2, then notice our first parenthesis will be a negative, but our second parenthesis will have switched to positive. So just as we expected, our signs are alternating. And if we choose a very large positive number, of course, both of these parentheses are positive. So then f prime of x is back to 0. So when our first derivative changes sign, that's our first derivative test. So what we've noticed here is that where f prime changes from positive to negative, so right between these 2 points, or right in here, if we have our positive slopes and then negative slopes, we have a local max at x equals 1, since f prime changes from positive to negative. That's what our first derivative test tells us. And right here, we know that there is a local minimum at x equals 3, since f prime changes from negative to positive. All right, well, look at our original function again. We have a cubic function, so we know by looking at the first term that this graph rises on the right and falls on the left. So you might want to make a note that there are no global extrema because of the leading term. So you don't need calculus to know that. All right, question 14. Now we have a closed interval. So we think of the closed interval test. So we know the closed interval test tells us that the global extrema can happen only at critical numbers or at closed endpoints. Well, this is the same function as up above here. So let me just rewrite our first derivative in factored form. So remember that our critical numbers, we had already found out, were 1 and 3. So our closed interval test says that our extrema, our global extrema, can only happen at the endpoints or at the critical numbers. So we can test the values here. And we want to make sure you go back to the original function. So you could grab a calculator, use your table feature, or you're in the home screen, but find all of those y values. So we've already found our local max and min where they occur from the previous problems. We knew that there was a local max at 1, and now we can see that that is not only a local max, but it is also a global max, and it also occurs now on the closed endpoints. So we know that we have a global max of 4 at x equals 6. We have a local max of 4 at x equals 1. Global and local, I should say. And we have our global and local minimum. Nope, just global. It's at an endpoint. Global minimum of -14 at x equals -1. All right, so what about this point at 3, 2? Well, remember that was from our previous problem, that was a local minimum, so we could add that to our list. A local minimum of 2 at x equals 3. We had already found out in the previous problem that that was a local minimum. So I think we've covered all the extrema there. All right, let's practice the second derivative test. So our first derivative of this function would be 4x minus 4x cubed, and we could factor that. 1 minus x squared, so we can factor again. And we'll have 3 critical numbers. And if I list them in order, -1, 0, +1. And our second derivative, so those are the places, this is where f prime of x is equal to 0. There's no undefined values. F double prime, let's go one step farther, so let's use our f prime and do the power rule again. And we might find it helpful to write this in its factored form, so that would be a 1 minus 3x squared if we factor out the 4. All right, so now we want to find the value of f double prime when f prime is equal to c. So I think I'm going to be even more specific than my directions. F prime of -1 equals 0, and f double prime of -1. Let's plug it into our second derivative, and I guess we could plug it into either the factored form. So we would have -8, and we want to identify local extrema. So remember what this means. We have a horizontal tangent, and when the second derivative is negative, that means that it is concave down. So again, think about it, concave down with the horizontal tangent. We are at a local maximum. So f has a local max at x equals -1, and you'd have to plug it into the function to actually find what the y coordinate is. Let's test our other values. F prime of 0 is equal to 0, and f double prime of 0 is equal to 4. So now it's concave up, so that tells us f has a local minimum at x equals 0. And one more to test. Our critical number from up above, f prime of 1 was equal to 0, and f double prime of 1 is 4 minus 12, or -8 again. So you could combine these. If you did this again, you could do both of these at the same time. So you don't have to write your justification twice. So it has a local max at x equals 1. All right. And we could add that this is by the second derivative test. By the second derivative test. That's the name of a theorem, by the way. All right. Locate the points of inflection and concavity. All right, so we've kind of done our work already. Here we have our second derivative, so f double prime of x is equal to 0 when, and now we could use our factored form here, is equal to 0. So that would mean that 1 would have to be equal to 3x squared. So that would be plus or minus the square root of 1/3 is where the second derivative hits 0. So then we would have to test our intervals again. So on the interval from negative infinity to negative square root of 1/3. And on the interval from positive square root of 1/3 to infinity. Think about testing both of those. Can you see that those would be the places where our second derivative would be less than 0? So f is concave down since f double prime of x, just a little more space here, is less than 0. And in between, on the interval from the square root of 1/3 to the, from negative square root of 1/3 to positive square root of 1/3. And you can try this. Try 0. Put 0 into our second derivative. Go way back up here. Let me point up here. There's our second derivative with the blue arrow. If you put 0 in there, do you see that f double prime is positive? So I can go back and complete here. So f is concave up since f double prime of x is greater than 0. All right, so we have to test the intervals to know that. All right, so we didn't actually answer the inflection point. So what we've just shown is that we had a change of sign of the second derivative. So f has inflection points at x equals plus or minus the square root of 1/3 since f double prime changes sign. So now I think we've answered all of the questions. All right, moving on. 16. Find the intervals where we have increasing and decreasing functions. So we can use our first derivative. So let's do our power rule here. And let's factor that for x, and then we'd have x squared minus 1. So easily factorable. So our critical numbers, the places where f prime is equal to 0, would be -1, 0, and 1. And think about testing your intervals here. Notice that we've got 3 factors now to test. So if you notice that there's no double roots, we're expecting the intervals to alternate. Well, if we pick a number that is smaller than -1, so just try it. If you put a -10 in for x, you'd have the product of 3 negatives. So we know that on that interval from negative infinity to -1, that f prime will be negative. And then it's going to alternate and be positive on the next interval. And you should double check that if in doubt. Put in a number like -1/2, and you'll see that the first term is negative, the second parenthesis positive, and the third is negative. So we're back to a positive. And then on the next interval, we'll go back to the previous, so between 0 and 1. So on these two intervals, f prime of x will be less than 0. So f is decreasing. And on the other two intervals then, f prime of x is greater than 0. So f is increasing. So what we've just found then also can help us then. We can locate the maxima and minima by that first derivative test. So we started out with a decreasing function, and then at -1 it changed to increasing. So negative slopes to positive slopes would give us a local minimum. So f has a local min at x equals 1, nope, sorry, -1. And then it did the same thing, changed from decreasing to increasing at +1. So I guess I could just put plus minus 1 here. But we want to justify, since f prime changes from negative to positive, and f has a local maximum at x equals 0, and that's where we changed. It was positive, it was increasing, and then switched to decreasing. So it's a local max at 0 since f prime changes from positive to negative. That's our first derivative test, remember? All right, concavity, let's go to our second derivative. So go back to our first derivative and do the power rule yet again, 12x squared minus 4. And if we factor that, we'll have a 3x squared minus 1. So f double prime of x is equal to 0. This is just like our previous problem, it looks like. And remember, it's not enough for the second derivative to hit 0. We have to test our intervals. So if you think about choosing a number that is very negative, think of a number like -10 or +10. Can you see that the second derivative would be positive? But between negative square root of 1/3 and positive square root of 1/3, a number like 0, if you put 0 in for x, can you see that the second derivative would be negative? So we know what's happening on the intervals here. So we could say on -infinity to negative square root of 1/3, and we could use a union symbol, or you could say and. On the interval from 1/3 to infinity, f is concave up, since f double prime of x is greater than 0, and that leaves the interval between them. I didn't leave you much space to write here, sorry. F is concave down, since f double prime of x is less than 0, and that means that we have inflection points. F has inflection points at x equals plus or minus the square root of 1/3, since f double prime changes signs, or you can say since concavity changes. Means the same thing. All right, lots of problems here. Find increasing and decreasing again. F prime of x is 6x squared plus 6x minus 36. And let's write it in factored form. X plus 3, x minus 2. So our critical numbers will be at -3 and +2. And let's test our intervals. Again, they're single roots, so you expect the intervals to alternate. So from -infinity to -3, and on the interval from 2 to infinity, let's think what will happen with f prime of x. So if you chose a very small number, -10 again is a good example. We'll have two negative factors, so f prime will become positive. If you choose a number larger than 2, both factors will be positive. And on the interval between -3 and 2, f prime of x will be less than 0. So we could add our conclusions here. So F is increasing, and here, so F is decreasing. And of course then that's answering our local extrema questions. We know that we started out with F prime rising and then it fell. So we know that F has a local max at x equals -3. Let's put a D there for an and. And I'm pausing here thinking that perhaps I should remind you that we could actually plug -3 into our original function. So we could say a local max of 81 at x equals -3. Since f prime change from positive to negative, and f has a local minimum at x equals 2. And I went back and did some computation, -44 at x equals 2, since f prime changes from negative to positive. So again, this is the first derivative test. All right, concavity. Got to go to the second derivative. So we'll have 12x plus 6, and we can see that f double prime will be equal to 0 when 12x is equal to -6 or x is equal to -1/2. And does it change signs? Well, let me double check my factoring there. So if we have a number smaller than -1/2, then our second derivative will be negative. So on the interval from -infinity to -1/2, f double prime of x is less than 0. So f is concave down, and on the interval from -1/2 to positive infinity, f double prime of x is greater than 0. So f is concave up, and I didn't leave myself space, so that means then that f has an inflection point. And you could take the time here to plug in the -1/2 into your original function and actually give the both x and y coordinates of the inflection point. But I'm not going to pause to do that here. This is getting very long. Since concavity changes or since the second derivative changes signs. Your choice. All right, so suppose f double prime is continuous everywhere. If the first derivative equals 0, that's our horizontal tangent. And the second derivative is negative. That means that f is concave down. So by our second derivative test, this means that f has a local max at x equals 2 by the second derivative test. How can you have a horizontal tangent in a concave down section? Just always think of that picture. Where can you have a horizontal tangent in a concave down section? So you don't have to memorize that. So likewise here we've got a horizontal tangent when the first derivative is equal to 0 and the second derivative is equal to 0. So what can we say about f? It may or may not. It may or may not have a local extrema. local extremum. I guess we want singular. Remember, it could have a saddle point, just an inflection point, but it might not have a max or min. All right, and we got one more here, which I'm going to pause and enlarge a bit. And this question is getting at concavity and how it impacts things. So if we're talking about temperature at time 3, so notice our x-coordinates here are all at time 3 in our first derivative and in our second derivative. So think what we know at time 3, if the first derivative of the temperature is positive, the temperature is increasing. The second derivative is positive, so the temperature graph would be concave up. So increasing and concave up. So that would tell us the temperature is increasing faster or at an increasing rate. Temperature is increasing at an increasing rate. So if you were already feeling too hot, you would not like that. And here in the next situation, f prime is positive, so our graph is increasing, but our second derivative is negative, so it's concave down. So the temperature is increasing at a decreasing rate. So I don't like it, but it is not going to make me as uncomfortable as the first case. All right, and then if our second, in case C, if our temperature is going down when our first derivative is negative, so temperature is decreasing, positive second derivative, concave up. So think of the shape here, decreasing but concave up. And then of course our last situation is decreasing and concave down. So here the temperature is decreasing, and here it's decreasing quickly at first and then slowing down. So at a decreasing rate, but it's decreasing quickly at first, so I think that's what we like about that one. If we were already feeling too hot. And here the temperature is decreasing at an increasing rate, which means that at first it's decreasing slowly. So I think that choice C is the one that would make us feel the best. All right, too many review problems for you guys, so I think I have to cut back in the future.